Okay, so let's start with what is AV? Well, in the simplest sense, AV is audio and video. But given that we're Brompton, our passion, as you might expect, is rather for the video side of things. So that's what we're going to focus on here. So what is video? Well, it is essentially a sequence of frames or images that change over time. And by displaying them one after the other in rapid succession, we get the impression of movement, we get a video. So okay, video is a series of frames. What are those frames made up of? Well, if we take a look at one of those in detail, we're going to start to see that it's made up of a series of pixels. And the pixels within our image, we like to think of as having a specific order, which we call raster scan order. And raster scan order starts at the top left, runs through the first line, jumps back to the left-hand side for the second line, and then carries on, just like this. And it's important that we know what order we're dealing with our pixels in, because we'll need that information to be able to reconstruct the signal later on. Okay, so video data then is a stream of pixels in a known order. And for each of those pixels, we're going to need to encode it in a known way. So the way that we choose to do this encoding, we decide channels that we want to use. So for example, we might say each pixel we're going to break down into its constituents in terms of the red light, the green light, and the blue light. So we have 3 channels. There are other ways of doing it. And we're going to say, for each of these channels, well, how are we going to represent that signal digitally? How many bits are we going to use for each of those channels? And it's important to recognize here that what we're talking about is encoding rather than compression. So just to clarify briefly, encoding is essentially taking those real-world values, so amounts of red, green, and blue light, and turning them into a digital signal that represents those real-world values. Compression is a little bit different. It's about taking the digital signal and saying, gosh, there's a lot of information there. Can we squish it down in some way so that our bandwidth is lower, because that's convenient? So we're not going to worry too much about compression here. We're very much talking about how we encode the signal to transmit those pixels over a network. So each pixel gets encoded, but we need a bit more information to be able to understand then how to turn that back into effectively light. So we need 2 things. The first is we need to understand what's called an EOTF, or electro-optical transfer function. And this essentially gives us the relationship between the value that we've encoded and how much light there is. You might assume that if we've encoded a value as 50%, that means there's half the amount of light. And that isn't necessarily true. In fact, typically it isn't. And it depends on whether we are working with SDR content and using a gamma curve, or whether we're working with HDR content, be it PQ or hybrid log gamma. So we need to understand how to unpack those pixels back into real-world values using that EOTF. The other thing that we need then is to understand the color space or color gamut that we are working within. So we know that we've got red, green, and blue, but exactly what red is it? How broad is that color space? Are we working with a very broad color space that will support saturated colors, or are we working with a much narrower color space that's all about paler colors? Again, we need this information to be able to interpret the signal and to turn it back into light. Okay, so that's what the video data is. But we've also got to think about the timing of the signal. And there are 3 parts really to consider when we're talking about video timing. So the first is the frame rate. So essentially, how quickly are we advancing from one of those images to the next? So that might be 60 frames per second, which means that we are going to transition from one image to the next image every 60th of a second. Okay. The next thing we need to think about is phase. So 60 frames per second tells us how quickly things are happening, but it doesn't actually tell us when the first thing happens. So thinking about trains for a moment, we might say that there's going to be 1 train an hour. And that's essentially equivalent to our frame rate. So we know how often these things are going to happen. But it doesn't tell me when the train's actually going to arrive. So to know when the train is going to arrive, we need to know, oh, okay, it's always going to be at 1/4 the hour. And that 1/4 the hour is my phase information. So the frame rate and the phase together tell us exactly when each of those frames will arrive in time. Okay, what about within a frame? There are lots of pixels within a frame. We know that they are in a particular order, raster scan order. When are they expected to arrive? Well, we need to have a concept of raster timing. And the raster timing is all about saying, okay, when am I transmitting pixels, and when am I waiting between this frame and the next frame? And it typically looks something like this. So we'll transmit an entire frame of video, and then there'll be a short pause, and then we're going to start transmitting the next frame of video, and that repeats. So 3 elements to timing for video. So digital video then is pixel data in a known format and timing. But there's one other thing that we need to consider as well. Now, normally, such a signal would be sent over something like a baseband connection. We're also going to talk about situations where that isn't the case in a minute. But if we think about something like HDMI, well, the HDMI standard covers pretty much everything that we need to be able to interpret that video signal. So it covers everything from the exact connector format through to the electrical details of the signal. There's interoperability mechanisms all built into the standard. And ultimately what that does is it makes sure that if you have 2 HDMI devices, at least in theory, there is a good chance that you can connect them together and they will now have a shared interpretation of that video signal, which means that the receiver is able to reconstruct the signal in a way that the sender intended. So, AV, for us, is data, timing, and a shared interpretation shared by the sender and the receiver.